I don't know if you recall, but I ended last day, I said, if you're in a car, your body is a backwards accelerometer. Whichever way the car is accelerating, you feel like you're getting pushed in the opposite direction. And that's because you're actually feeling your body's inertia. Your body wants to stay at rest or keep going in a straight line at a steady speed. But I said to you, there was a fairly common, ordinary, everyday device that if you have it in your car, when you step on the brakes and you're accelerating forwards, it will point forwards in the direction of acceleration. And when you hit the brakes, which means you're accelerating backwards, it will point backwards. Oh, and when you go around a corner, which means you're accelerating inwards, it will actually point inwards. What is that common, ordinary device, you ask? 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 Well, I'm so glad one of you asked, but I was kind of hoping for a little more call and response from the back row there. Put your pencils down and look up.
Hey, it's me, Destin. Welcome back to Smarter Every Day. So today we're in the rocket van, and I've got two little science helpers here, right?
Yes.
Are you wearing your seatbelts?
Yes.
Okay, we're going to do something pretty interesting. Check this out. I've got a pendulum suspended from the top of our family van, and we're just going to drive forward. We're going to accelerate. So if we're going that way, which direction do you think this pendulum should go? What do you think?
So, first of all, just a hanging mass. If we step on the gas so we're accelerating to the right, which way do you think the hanging mass is going to point? What do you think? Yeah, it's got inertia. It's going to point to the left. This is not the common, everyday, ordinary device.
3, 2, 1, go.
Yes.
Which way is it going?
My way.
That's right. It's because I'm accelerating, right?
When he hits the brakes, I think we'll see it point forwards in the opposite direction of acceleration. The same way we are backwards accelerometers, so is that.
Does that make sense to you guys?
Yes, sir.
Okay, very good. I was hoping it would make sense. So we're going to change it up just a little bit. Okay, so now what I'm going to do is I'm going to replace this pendulum with a balloon. We should see the same thing, right? Let me cut this off. So what we're going to do is we're going to accelerate that way. So we have the mass of the balloon and the acceleration, so that should net in a force, and we'll have to react with this string, right? You guys ready?
Yes, sir.
3, 2, 1, go.
It's pointing in the direction of acceleration. What do you think will happen when he hits the brakes and starts to slow down? It will point backwards.
Wait a second. What just happened? Oh, what happens when I stop?
Okay. A helium-filled balloon will point in the same direction as acceleration. It acts as an actual accelerometer. So here's the question I have for you. Why?
The balloon goes backwards when I stop. What's happening?
It's doing the same.
3, 2, 1, go. There it is. It's coming right at me. Why is it doing that? Do you want to know?
Why will a balloon point forwards in the direction of acceleration when you accelerate? And why will it point backwards in the correct direction of acceleration when you slow down? What's going on there? That's a question we are going to ask you to answer. So that's not like the previous one where I kept repeating myself. What do you think? Didn't work with the pendulum. Why is it working with the balloon? Yeah, Clody. Does it have to do with its mass? Can you elaborate on that?
Well, the
Pendulum has a heavier mass.
It has more mass, so it has more inertia.
Okay. I like where you're going, although I think remove the pendulum. What if I just hung a string? When I stepped on the gas, which way do you think the string? I think the string would also swing backwards like the pendulum. It might not be quite as noticeable, but I think the string, which has less mass than the balloon, I think would still behave the same way. So I like your idea, but I'm not convinced that that's it. How is a balloon different from a pendulum? Mass is one, but how else? A helium-filled balloon. How is that different from a pendulum? Okay, it floats. It doesn't. You think it floats. Now I'm going to be a little bit fussier. What a helium balloon tries to do, it tries to go to an area where air is less dense. And air is less dense above us. You've learned that. If you're on Mount Everest, it's really, really tough to breathe because the air is less dense. You okay with that, Cole? All right. But now the balloon is inside an enclosed room, a car. When the driver steps on the gas, the air itself has mass. It has inertia. It sloshes to the back. Now, you can't feel that on your skin. It's not that noticeable. But I'm telling you, while he's stepping on the gas, there is slightly more air in the back than in the front. It's slightly more dense in the back, less dense in the front. And I've told you, helium balloons, they don't actually float. They seek out an area of less density. It's less dense in the front, and so it's going to point to the front. What about when he steps on the brakes? The air sloshes forwards, and now it's more dense slightly in the front. Where will the balloon point then? Where it's less dense, towards the back. This is measuring the sloshing of the air. Even though your skin can't feel it, the balloon detects it.
Yeah.
I brought something to show you. You remember I told you I was going to bring this jar earlier? Remember that? So it's like this. Imagine this entire van is just like this jar. And all the air inside this van is just like the water in the jar. Does that make sense? So let's imagine that the balloon is this bubble on top. Because the helium in the balloon is lighter than air, right? So that causes it to do what?
Go up.
Go up.
Head to a less dense area, if I'm being really fussy.
That's right. So if I've got this air that's just like it, what happens if I move the jar that way? All that water sloshes to the back. And when that water sloshes back this way, which direction does the bubble go? You see that? So the air bubble moves in the direction of acceleration. Does that make sense? I know you're 5, but I think you can get this. Okay, so I've got my seatbelt on. If I drive forward real fast right now, which direction is the balloon going to go?
Which direction will the balloon point if we accelerate forwards to the right? Forwards to the right.
Forward.
Why will it go forward?
Because all the air is splashing back.
That's right. Very good. Watch this. Look at that. You see that? So you know what that means, don't you?
Also notice now he's turning a corner. Which way is the balloon pointing? Inwards. When you're turning a corner, which way are you accelerating? Inwards. If you are ever in a car and you have a party helium balloon and you're not the driver, talk your driver into doing this. Go into an empty area of the parking lot and you can try this and you'll see this absolutely works. I encourage you, try the experiment. Okay? Pause for a second. I like the free body diagram of example 8. It says this: a 540 kilogram dragster's tires accelerated from rest. I'd probably mentally underline the word from rest to a speed of 48 meters per second. I'm already thinking that I'm going to find A, if necessary, using VF and VI and D and T, just as soon as I saw that information. In a distance of 64 meters. Eric, what does part A want me to find? No, part A. Part A. The acceleration. I don't think I'm going to be doing a free body diagram, Winner minus Scott's theorem. I don't think I'm going to be doing that. I'm pretty sure, looking at the information, I'm going to go, well, A equals question mark. Eric, from rest, what does that tell me? 0. What about that 48? The F. And then what's that 64? Yeah. We're on old familiar territory. Looking for an equation that's got an A, a VI, a VF, and a D. Eric, my friend, there is one somewhere. VI squared. Can you get the A by itself? And I'm so lazy, I'm even going to do that since VI is 0. Yeah, well done, well done. Are we speeding up or slowing down? Am I expecting a positive or a negative acceleration? Yeah, if I got a negative, I'd panic a little bit. I did something wrong somewhere, right? So some built-in error checks. It's going to be 48 squared all over 2 times 64. What do you get, folks? Get out your calculators. Follow along. Brackets around the bottom, definitely. I get exactly 18, which is just under 2 G's. That's probably about right for a dragster. Maybe they might pull 3, maybe a bit more. I don't know. I was making these numbers up. I didn't go do a Google search on dragsters and try and get the numbers accurately. So, Eric, I agree with you. 18. Eric, units? It's an acceleration. Good. Excellent, excellent, excellent. Sophie, what does B want me to find? The what force? The what force? If I see net force, I can go straight to F equals ma. Do a quick check. Sophie, do I know M? Yeah? Do I know A? So I would have, after today, no problem on a quiz or a test, not asking part A for Eric, going straight to part B and just saying find the net force, and Eric expecting you to realize, oh, I got enough here to find the acceleration. I can do this. Okay? So it's going to be 540 times 18. Or I should have used my answer button. I get 9,720 newtons of force. Cool. Ella, what's C want me to find? Well, my first thought would be friction is what times what? It's on your green sheet. Mu times the moment force. Okay, don't write this down. My first thought would be this. Why doesn't that help? I don't see a coefficient of friction anywhere. In fact, what's D asking, Eric? Oh, okay, then I can't use this. In fact, I bet you I'm going to have to find friction another way, and then in D, I'll get the mu by itself. Follow me? Okay. Any suggestions, Ella? I think I might try a free body diagram. I mean, got nothing to lose. We haven't done one yet. There's several forces going on here. I'm going to do my free body diagram over here on the right. I'll do it in red. Okay. What are the forces acting on this dragster? Get the obvious one. Which way? Good. What else? Bigger, smaller, or the same size as mg? Pretty sure. What else? That's a good question. Well, which way are we accelerating? To the right? Which way does there have to be an unbalanced force then? What force is that? What force causes a dragster to accelerate? What? Loud and proud. Friction. This is the free body diagram. This is the one that I think I told you I was at a physics conference and a physics teacher got wrong. Don't write this down. They had this. They had F engine and they had friction pointing that way. And I had to, no. If that was the case, cars could drive on ice. In fact, they would drive better on ice because you'd have no friction slowing them down. Do cars drive better on ice? Because they still got their engine. So, this is what I want you to realize. For a car, friction. And that's it. By the way, if I was really fussy, maybe a bit of air resistance pointing backwards, but did this question say include air resistance? If it doesn't say to include air resistance, you could ignore that. Yeah.
Is there no fourth arrow? Because I thought forces
Okay, that's a great question. Forces come in pairs, but they don't come in pairs on the free body diagram. This is what you asked me. So you ready? Which way are the tires pushing? To the, I'm looking for where that starts with the letter L. Okay? If I drew a free body diagram of the road, that's the pair that goes with that. But it's not on my free body diagram because am I drawing a free body diagram of the road? No. What am I drawing a free body diagram of? The dragster. But that is the action-reaction. For every action there was an equal and opposite reaction. That is the opposite pair right there. The tires push on the road, and the road, through the force of friction, pushes back on the tires. Is that okay? That's a great question. Okay. Well, let's try writing an equation. Which way are we accelerating? To the? Which way is the winning direction? To the? So who's winning? Friction. Who's losing? It's a trick question. Who's losing? Losing would be anything pointing to the left. Who's losing? Someone say it. Nothing. So my equation here, which starts out looking really complicated, but actually no, for a dragster, friction equals MA. Winner, no loser. I see a few of you smiling because you may have seen it. Ella, do you see it? What's MA? 9,720. In fact, I'm done. I knew friction all along without realizing it because friction is what's causing the net unbalanced force here. Cool. Okay. Scott, what's D asking me to find? Now I'm going to write friction is mu times the normal force, because this is actually saying, hey, what's mu? I don't know, what's mu with mu? Yeah, this is saying what's mu. Okay, folks, how would I get the mu by itself? Aiden. Divide what? Okay, so you're telling me the coefficient of friction. So we could use this if we were designing dragster tires. We would say we need a minimum coefficient of friction of this. Otherwise, we can't get this acceleration with this dragster. It's going to be friction divided by the normal force. Friction is 9,720. Scott, I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. What? 9.8 is not the force. What is gravity as an equation exactly? Yes, you do. mg. Don't just put a 9.8. You got to put mg there. So it's going to be answer button divided by bracket. What was M? 540 times 9.8. And I get a coefficient of friction of 1.8. We did say yesterday dragster tires can have coefficients of friction bigger than 1 because the more friction, the better force, the more force they have to accelerate them. In fact, I think I told you, we said yesterday, they increase mu by doing a smoke show because, what? Melted rubber is stickier than cold rubber. So 1.84? Units, newtons? Oh, nothing. This is not a force. This is a unitless ratio. Cool. I think we're almost done. Yeah, one more, we're done. This is about as tough a question involving friction as I can throw at you. If you're asking me what would I consider an A or even an A+ level question, here. If the mass below is accelerating to the left, okay, at 1.2 meters per second squared, Acacia, what's this asking me to find? Guess it wants me to get the mu by itself. Okay. I'm not going to panic. Any thoughts on how I might want to start this? So what do we call that? Something. Okay, let's and then she said gravity. Yeah. Did they give me a picture? So unlike the previous one where I just represented the mass with a dot, I'm going to be lazy and I'm going to label the picture. All right, what are the forces acting on it? Get the obvious one. Good. What else? I always do normal force next. Is the normal force here going to be bigger, smaller, or the same size as gravity? How do you know? It looks like someone's lifting up with 85 newtons, and so the normal force isn't having to cancel out all of gravity. I'll really exaggerate it so it catches my eye. What else? We have F applied. What else? But we've got one more force, and it's so obvious, it's tricky. Which force do we need to put on here still? Got to be friction, because they're asking me to find mu. And friction, now it says it's accelerating to the left, but I think it's moving to the right. So which way is friction going to be pointing? To the left. By the way, friction, bigger, smaller, or the same size as F applied? Bigger. In this case, friction is causing this to slow down. I'll try and exaggerate it so it's really obvious. Because now, Acacia, in my equation, you're correct. Which way are we accelerating? To the?
Left.
Which way is the winning direction? Same answer.
Left.
Who's winning? Friction. Yes? Who's the losing force then? Yes. What's that always equal? Good. What's this question want me to find? It wants me to find the coefficient of friction, which I think is hidden inside there when I say friction is what times what. So I'm going to get friction by itself first. How would I move the F applied over? Yep. I'll get this. MA plus F applied. I'm going to do one more thing. Instead of having friction drop down like a domino, I'm going to have mu times the normal force drop down like a domino, because that's what I would have substituted in for friction on the next line. What am I trying to find? What's mu? I don't know. What's mu? How would I get the mu by itself? Yes? Now, normally I would say I don't know the normal force. Oh, but look, this is a more complicated one because the normal force is not mg. So I'm going to press pause, and over here I'm going to write a vertical force equation. Are we sinking into the ground like quicksand, Ella? Say no. Are we flying into the air like Superman? So what that really means is everything down has to equal everything. Can you give me a vertical equation? In other words, can you say everything down and then put an equal sign and then say everything up? Yes. Nice. I want the normal force. How would I get the normal force by itself? Okay. So I can stick that right there. Now I think we're ready to start plugging in numbers and get an answer. So mu is going to be, Acacia, what's m? 20? I've scrolled down. What was a? Do I need to make that negative because it's to the left? Actually, no. We decided to make to the left positive because it made the math easier. And this is why I've been telling you this unit, we don't need to put negatives and positives in for acceleration. 1.2? And then plus, what was F applied? Good. All divided by, and then the normal force is going to be M, 20, G, 9.8, minus 85. That's one that's worth trying to type in on your calculator because you've got a complicated thing on the top and a complicated thing on the bottom. What do you get? 20 times 1.2 plus 75, that looks right. 20 times 9.8 minus 85, that looks right. Ooh, you get 0.892? This is really, really grippy. Yeah, that's why the box is slowing down, because you're pulling it actually. 70, that's a pretty good applied force. Nope. Turns out this is so grippy, maybe this is on sandpaper or gravel, that this person is losing. This box is going to slow down, slow down, slow down, and eventually come to a stop, unless they pull harder. 0.892. Well done. You handled an A+ level question. Okay. What's your homework? So first of all, this free body diagram here, where friction is what's causing you to accelerate when you're a car, is going to be really handy for some of the questions I've put a star next to on lesson 5. Oh, by the way, what about when the dragster hits the brakes, or when a car hits the brakes? What's that free body diagram? We still have mg. We still have normal force. If they're slowing down, which way are they accelerating? If we're slowing down, which way are we accelerating? Looking for, yeah. Which force slows you down? That's for braking. And the way I know that is if we put you on ice, braking doesn't work anymore. It's because there's less friction. So when you're talking about a car, friction makes it go forwards. Friction makes it come to a stop. When you're talking about riding a bike, friction is what makes the bike go forwards. You do a complicated series of forces through the pedals, but eventually it comes down to, just like in the dragster, the tires push backwards on the pavement, forces come in pairs, friction pushes the tires and the bike that they're attached to forward. Oh, and then when you hit the brakes, what you're really doing is you're causing the tires to apply a forwards force to the pavement. Friction is what brings the bike to a stop. That's why you can skid. When you skid, you demanded more of friction than it was capable of, so Newton's first kicked in. You kept going in a straight line at a steady speed, although you'll slow down a little bit because there's still a slightly unbalanced force through the skid. Okay, what's your homework? Lots of practice. Number 1, 2, 3. 3 is so easy that it's tough. By the way, 2 and 3, no friction. Those are just generic, but you're going to do a free body diagram. Now we're getting into friction. 4 is good. 5 is good. 6 is good. 7 is good. 8, 9, and 10. Yeah, I assigned all of them.